Section 1.1, Problem 18. So in this problem, once again, you're given a story, and they're asking you to find some functions that you're supposed to extract from this story. So the idea is this. You have an airplane. It takes off from one airport and arrives at another airport 1 hour later. And this other airport happens to be 400 miles away. So now if t represents the time in minutes since the plane has left the terminal building, then you're asked to sketch a couple of graphs. So for example, part A, you're asked to sketch the graph of x of t, where x of t is the horizontal distance traveled. So let's first focus on A. So first, the important thing is we need to draw out our axes. So what's the x-axis going to be? Well, everything is sort of based off of time. So again, t is going to be the x-axis in this case. Now, t is in minutes, so let's just write that in parentheses so we remember that. And recall, what is the duration of this entire flight? Well, it's 1 hour, so it's 60 minutes. So let's just draw a tick mark somewhere out there to represent 60. Now, what are we modeling? We're modeling the distance traveled. So the y-axis is going to be x of t. Recall, this is not the same thing as the x-axis x, it's just distance. So just going to keep that in mind. This is just miles, basically. And recall that that airport, the airport that you're arriving at, is 400 miles away. So let's draw a little tick mark at 400. So our goal then is to draw out a graph that could possibly represent the airplane's distance, horizontal distance over time, as it's traveling to that airport. So first of all, we have 2 points that are definitely fixed. So one of the points is the origin, right? Because after all, at time 0, where are you? You're at the original airport. So you're 0 miles away, and the time is 0. Now there's another point that we also know for sure, which is what? Well, we know that in 60 minutes, that airplane is going to be 400 miles away at the other airport. So that means the other point that we know for sure is this point. Now, in between, we have a lot of freedom. But since our goal is to sort of model this situation realistically, I'm going to draw a particular graph and explain why this might give a reasonable story. So if you look at this graph, what's the first thing you notice? Well, it's increasing. What does increasing mean in this case? Well, increasing just means you're getting further and further away from the departing airport, and you're getting closer and closer to the arrivals airport, which of course is reasonable. If after all you're in an airplane, you're flying from one airport to the other, you would expect that over time you're getting closer and closer to the arrivals airport. But there's more to it than that, right? If you look at this graph, it's not just a straight line to 400, it kind of curves a little bit. So for example, in the beginning, it sort of bows outwards. What does this mean? Well, this means that at the very beginning, the distance that you're traveling is very little, and as time passes, the distance that you're traveling gets greater and greater. What does this correspond to? Well, if you recall, you start in an airplane, that airplane isn't going to suddenly start flying at 800 miles per hour, right? It's going to take some time. So in the beginning, it's going kind of slow. That's why it's kind of flat there. Now in the middle of the course, say 30 minutes into the flight, well, that's when the plane is going the fastest, and that's why the slope of the graph is the steepest, around 30 minutes, signifying that the plane is moving at its top speed. And then notice what happens towards the end. It starts flattening out again. And of course, by now we know what that means, right? Well, the airplane is slowing down to arrive at the destination airport. So there are flat pieces in the beginning and the end of the graph that represent the airplane slowly speeding up and slowly slowing down. And then there's a steep portion in the middle that represents the airplane flying at its maximum speed. So that's part A. Part B. Part B, you're asked to measure another quantity. And this quantity is, they define it to be y of t, and it's going to be the altitude of the plane. So once again, first thing that we do is to draw out the axes. T is still going to be, the x-axis is still going to be the same. But now, the y-axis is going to be altitude. And we're not given any specific altitudes, so we could just sort of make something up that's might be reasonable. So let's measure this in miles as well. And suppose a reasonable maximum altitude might be 6 miles. Okay. So how would we imagine this graph to look like? Well, again, just think back to the realistic situation of an airplane going from one airport to another. So in the beginning and the end, what's the altitude of the airplane? It's got to be 0, right? It's not above the air at all. So we know these 2 points. And then everything in the middle, it's up to us to sort of figure out. So we can imagine that the airport so what happens to the airplane in the beginning? Well, it starts ascending, right? So its altitude gets greater and greater and greater until finally it reaches our cruising altitude, which we've assumed in this case to be 6 miles. So what happens? Well, it stops ascending. And of course, it doesn't also come down. It just sort of stays there for the duration of the flight. And then as the airplane is nearing the destination airport, what happens? Well, it's got to start descending. So it descends all the way until it's back down to 0 again. So this is one possible graph that represents the altitude of the airplane. What else? So in part C, we are asked to represent the ground speed. So once again, everything is going to be in terms of t, so the x-axis is still t minutes. Duration is 60 minutes. Let's call the ground speed capital G. So that's going to be our y-axis. So how could we model the ground speed? Well, again, why don't we just fix some sort of cruising ground speed, say G, which would be, I don't know, it could be, for example, 600 miles per hour. Right? Now, using sort of the argument that we've made before, we know already 2 points, the end point and the beginning point. What's the speed of the airplane right when it starts? Well, it's 0, right? So here's 1 point. And of course, once the airplane arrives at the destination airport in 60 minutes, what is its speed? Well, it's 0 again. So here we have another point anchored. And in the middle, we just have to draw a graph that corresponds to a realistic story of the airplane. So is going to look kind of similar to the altitude case. It starts off at 0, but what is the airplane doing? It's got to accelerate. So it's accelerating, accelerating until finally it reaches about 600 miles per hour. And then it's reached its cruising velocity. So it just sort of goes at that point until finally it needs to start slowing down because it needs to land. So it slows down until finally it's at 60. Finally it's at 0, excuse me. So that is the ground speed. Next up, we have, in part D, they ask us to find the vertical velocity. So V is going to denote the vertical velocity. What is the vertical velocity? It's how much the airplane is changing in terms of its height. Now this one is interesting because we're going to actually have to use negative values. And before we draw out the graph, let's think about why we would need to use negative values. Well, if the airplane is going to go up into the air, what does that mean? That means it's changing its height in a positive way, right? Well, once it's in the air, eventually it's got to come down, right? In 60 minutes, when it lands, it has to decrease in altitude. So what's happening there? Well, it's changing in height, but now it's negative changes in height. So that's why whatever this graph is going to be, there's going to be both positive and negative changes in height. Here's t, here's 60. So once again, we have a lot of freedom in terms of how we want to draw this, but there's still going to be the two anchor points. And so what happens? The key shape is that it has to go up before it goes down, right? So the airplane starts at a state where it's not increasing in height. So initially it starts at 0, but then the airplane starts ascending, so it's positive now. And it keeps on ascending, but the ascending rate is smaller. Right? Eventually it's going to level off. So it's going to come down here. And then there's going to be a period where there's no changes in height. Right? And then it's going to dip so that it finally gets down to its original elevation. So this might be a little confusing because you sort of see that first thing and you're thinking, well, why does it go down and just sort of stay flat at 0? Keep in mind, V does not represent the height of the airplane, right? That's part B. Part D is representing the change in height, the vertical velocity of the airplane. So that's why when you're at 0, this flat part, which is at 0 here, it's not saying that the airplane is on the ground. It's saying that at that point there's no changes in height, right? You don't have to be on the ground to have no change in height. Just think about an airplane at cruising altitude. What's going on there? It's 30,000 feet above the air, but the point is it's not changing, right? It's not moving up, it's not moving down, it's just staying at 30,000 feet. So we represent that by a horizontal line at 0 because this is saying that there is a 0 change in height at that point. So this is the graph.